Hello, everyone. My name is Andrew Baker. I'm an alumni of Freedom Area High School, and today I'm going to be talking about the first year of my PhD studying material science. All right, before diving into the talk, I would like to just provide an introduction for myself and a little bit of motivation for the talk. I graduated from Freedom Area High School in 2015, and I also graduated from Clarion University with a Bachelor's of Science in Physics and minors in Computer Science and Mathematics in 2019. This summer, I'll be entering my second year of my PhD at the University of Pittsburgh. I'll be studying material science and engineering. And here I am in 2015 in the circle here attending the Trebuchet Day. This was way back in the day. Okay, so that's a little introduction about myself, some motivation for the talk. I would like to provide a focused look into higher education and STEM, and I want to do this through the scope of just kind of like a timeline of what how my first year went in my PhD. And I'd like to do this also to develop awareness of different avenues of study in STEM technology. So as juniors and seniors in high school are looking into college, I would just like to kind of make anyone who listens to this talk slightly more aware of different options. Okay, before going into my first year, I think it's important to address what material science is because there typically isn't really a high school course taught like that, even though there's a lot of materials chemistry and a lot of materials physics taught at a high school level. It's never explicitly called material science. So material science is essentially the overlap of certain disciplines in chemistry, physics, and engineering. And you can see here in this nice Venn diagram. And then within material science, there are different subdisciplines. There are people that study the structure of materials, the performance of materials, properties, and processing and characterization. And this is usually displayed by this tetrahedron on the right side of the slide. The tetrahedron just essentially represents how each subdiscipline is connected to each other, and yeah, that's just an overview of where material science lies in terms of other STEM disciplines, and then exactly how material science is laid out. All right, so now that we know what material science is, I think it's important to address the question, what is a PhD and what all does it entail? So a PhD is short for Doctor of Philosophy. It's a 4 to 6 year advanced degree. This timeline essentially depends on what research group you work in and the pace that they go. And this degree is usually completed after a 4-year bachelor's degree or a master's degree. STEM PhDs are typically funded with a stipend, and the pay is roughly $30,000 a year, depending on where your funding is coming from. So it's a nice livable wage. And then after you receive your degree, you are eligible for staff scientist positions, being an engineer at a company, working in R&D in a company. You could be a professor at a university. And also the skills you develop from this 4 to 5 years can transfer into other disciplines. So I know of a good handful of people going into data science. Some people are consultants, financial analysts, and there's all sorts of options. But after you receive the degree, the pay shoots up pretty nice. All right, so who can do a PhD? Anyone who finishes a 4-year degree in the field that they're majoring in. But before starting a PhD, you typically have to do a standardized test. This is called the GRE. It's basically an SAT for graduate school. Applying for a PhD can be very competitive, and it usually requires that you do undergraduate research and it typically requires a lot of preparation for applying to PhD programs. One important stipulation is that it does not have to be, you don't have to pursue a PhD in what you studied in undergrad. So for example, I studied physics in undergrad and I switched to material science for my PhD. And this is a really excellent point because this gives you flexibility to move around different disciplines and essentially follow your interests. So the big takeaway that I would like everyone listening to this to have is that you should absolutely be flexible in what you're studying, and you should follow whatever subject you're interested in, whether it's a problem like renewable energy, nuclear energy, or maybe you're just fascinated in quantum computing or coding or anything like that. Just find something you're very passionate about and follow it. Okay, so that essentially wraps up the background information necessary for this presentation. So now I'm just going to jump into the overview of the first year of my PhD. I started my PhD in the summer of 2019, and I began by developing background for my research project and adapting to my new environment. The overall process for beginning a PhD is typically that you join a research group and then you develop the background for whatever your project is and what your group specializes in. And then if you're an experimentalist, there's a lot of training on equipment that you have to do. So the main technique of the group that I joined is transmission electron microscopy. This alone, I could give like a 30 or 40-minute talk on. So I would just like to give just like a very low-level overview. Basically, a transmission electron microscope is just a fancy microscope that uses electrons instead of light, and it gives you much higher resolution. So for instance, on the right here, we see a nice image of a gold nanoparticle that I circled here in red. And it's sitting on an oxide surface, but the thing that I like to point out is that you can see individual atoms, and it has much higher resolution than your typical optical microscope. But what my group does is we will actually perform mechanical tests inside of the microscope or in situ tests. Okay, main application of my research is catalysis, which is the study of how catalysts affect chemical reactions. So a catalyst is any material that accelerates a chemical reaction. A common example is a catalytic converter. So that would be the figure on the right here. Essentially, those go on your car to clean the exhaust. So the way that it works is you have a system like this on the right that flows gas through it, and on the inside, you'll see I'm drawing here in red, you have gold nanoparticles on titanium oxide, and whenever these nanoparticles are mounted on the oxide, they become a catalytic material, and essentially they take carbon monoxide and add an oxygen and make it carbon dioxide, which carbon dioxide is a much cleaner gas in terms of pollution. So essentially, this catalytic converter accelerates the reaction. It accelerates the reaction and cleans the gas. Critical property of how this works is the work of adhesion, so how sticky the nanoparticles are to the oxide. And this is related to the particle growth. And as the particles grow, they lose their catalytic behavior and don't work as well. Okay, on this slide, I have a demonstration of how the work of adhesion is measured. First, in the microscope, we take a video of an AFM probe coming into contact with a metal nanoparticle. So it adheres to the metal nanoparticle, and then the work of adhesion causes a displacement, and then it pulls off. From the video we've recorded, we can determine a force of adhesion, which this is done by using Hooke's law, which if you've had physics 1 probably, you should know Hooke's law. It's just a spring constant times the displacement. So the AFM probe will have a spring constant that we'll know ahead of time, and then we can measure the displacement there to get force of adhesion. Then once we have the force of adhesion, we can use contact mechanics models to calculate the work of adhesion here. And there's a couple different models, but these are just the two relevant to this application. Okay, so that essentially wraps up summer 2020 for me. Fall 2019 was whenever my coursework began, and I was still continuing research. So the first course that I took was Intro to Material Science. This was for people that did undergrads in disciplines that weren't material science. So this is essentially just to catch everyone up to speed. So this covered concepts like material structure with crystallography, thermodynamics of materials, strength of materials, steels, and that sort of thing. The other class that I took was structure materials. This covers how atoms arrange themselves in crystals, and how to know crystal spacings, how to measure that, and that sort of thing. And we covered crystallography a lot, and I'd just like to point out that about 25 Nobel Prizes have been awarded for crystallography. I thought this was pretty interesting. It really shows how powerful this technique is. And then the last class I took was thermodynamics of materials, which that essentially connects the physics of thermodynamics to different material properties. And then with my research, I basically just kept working on TEM imaging. Here's an example of a video that I took while I was imaging. This is I essentially welded two platinum nanoparticles together by heating them with the electron beam. I thought this was pretty neat. You can see individual atoms, and you can see the crystals joined together. Okay, in the winter of 2020, after my courses wrapped up, I was able to go to a high-resolution transmission electron microscopy school at Arizona State University. It's in Tempe, which is like maybe 20 or 30 minutes outside of Phoenix. This was an excellent experience. I got to meet a ton of professionals in my field. I met people that work at different labs, like Los Alamos or other big national labs like that. I got to meet other grad students and socialize with them. It was just an awesome experience, and it was definitely one of the best experiences that I've had so far in my education. In spring 2020, I essentially had more coursework, continuing my research, and then I had a qualifying exam to become a PhD candidate. So the first course that I took was kinetics of materials. This is very similar to thermodynamics, but you're essentially adding the factor of time into the mix. So you essentially are tracking the concentration of a certain material as time changes, and how that works. So a lot of diffusion was covered in this course. Mechanical behavior of materials. This essentially explains how materials behave under stress. So if you pull on a metal rod, like what happens? Does it fracture? Does it stretch out? That sort of thing. Electromagnetic properties of materials. So in this course, we covered basically how electrons are able to move through materials and different unique properties that they have. We went over a lot of stuff with semiconductors, solar cells, and how different transistors work. At the end of the year, we wrote a nice paper on flash memory, which was very interesting. And yeah, so the 6 courses that I've described are essentially my core courses that every single material science major has to take. And then in terms of my research, essentially just continuing imaging and training, no really big developments because of the heavy course load and the qualifying exam. the qualifying exam is basically just a test to make sure that you qualify for PhD candidacy. The way that this is set up is that you need to propose an investigation that is related to your work, but not exactly what your PhD work is going to be. So, for example, I'm studying nanoparticle adhesion, so my qualifying exam presentation was to essentially just introduce gas and see how that affects the work of adhesion. And this is set up by you have to write a 15-page proposal, you have to do a 30-minute presentation, and then you have an hour and a half of questioning from professors and people on your qualifying exam committee. Okay, so to end the presentation, I'd like to just recap the first year of my PhD and give some takeaways of the presentation that I'd like to leave with everybody. Okay, so looking back, reviewing the first year of my PhD, I found that this was definitely the most challenging year of my education so far. However, I also found it to be the most rewarding as well. I think anything worth doing in life is challenging, and I think overall it's just been an awesome experience so far. I did notice that there's a huge increase in the rate of information that I'm learning. Like each of my the graduate courses are way harder than undergraduate courses, and on top of that, I'm also developing a background for research, so just a ton of information just being thrown at me constantly. But it's pretty great. That may sound discouraging, but like I said, I'm very happy with everything. And another thing is that I feel like with the pay of the PhD, I mean it's not great, but like I was able to live pretty comfortably on the stipend. And just some takeaways for students, juniors or seniors in high school looking to go to college. The number one thing that I'd recommend is to find a discipline or an area of a discipline that you're fascinated by, and then essentially tailor your education towards pursuing an understanding of it as best as you can. Anything that you find interesting, just go after it. And then once college starts, be flexible. So in my second year, I found that I really liked programming. So I picked up a minor in computer science, and that was one of the best decisions that I made in undergrad because it actually ended up opening a lot of doors for me in regular physics and material science. So basically, if you sign up for one major, there's no shame in switching around. And also keep in mind, college is very hard, and it may be very challenging at times, but anything worthwhile in life will be. Okay, so that essentially ends my presentation. So if you have any questions, please feel free to email me at ajb282@pitt.edu. Thank you very much for your time.